Welcome to week 5. Today we're going to be talking about series. So we're switching gears a little bit from last week. The first thing I want to talk about is why we care about series. Last week we were talking about differential equations. Sometimes when we set up a differential equation, the equation we get is difficult to solve in its original form. For example, if we're modeling the motion of a pendulum, we get a differential equation that looks like this. This comes from F equals ma and some geometry, and we'll actually go through this derivation in classical mechanics for educators. So when you get an equation like this is a pretty tricky differential equation to solve. And it would be easier if we could rewrite sine theta as some sort of polynomial. And what we do in practice is that we make this small angle approximation where sine theta is approximately theta. But if you need to go to large angles, then you'd actually want to use the full series expansion. Well, more terms of the series expansion. Another example of a situation where you'd want to use the series expansion is if you're modeling the vibrations of a diatomic molecule. So if you're looking at potential energy of a diatomic molecule, you get a curve that shapes something like this. Forgive my poor drawing skills. Well, one way of writing this function is like this, where x is your independent variable and delta and v naught are constants. So this is a function that represents this potential. Working with a potential that looks like this can be problematic. So what you want to do instead is write this function as a polynomial instead. So say we only care about what happens to the molecule in this region, then around here the potential is approximately proportional to x squared, and a series expansion is what is going to let you formally rewrite this potential as a polynomial instead. Okay, let's look at how we actually find series expansions. Remember, what we're doing is we're taking some complicated function and we're just going to look at that function in a narrow range and approximate that function as a polynomial. So when you're doing a series expansion around x equals 0, it's called a Maclaurin series. And so the formal way of writing out what a Maclaurin series is that you write out, you need to know what the value of the function is at x equals 0, what the value of the first derivative is at x equals 0. Remember, when we write this notation, that means the first derivative evaluated at 0. And we multiply that times x. Then we have a factorial. Then we have the second derivative evaluated at 0. Then the third derivative. And that just keeps going. And in case it's been a while since you've used factorials, that just means you do a bunch of multiplication. So 3 factorial equals 3 times 2 times 1. 6 factorial equals 6 times 5 times 4, etc. And when you get these, you don't need to multiply what these are out every single time. You can just leave it as 3 factorial. That's fine with me. So if we want to write this in series notation, and you'll have to tell me how long it's been, or if you have seen this kind of notation before. So this is just another way of writing this. So it means you add up for n equals 0 to n equals infinity all of these terms. So you have the 0th derivative, that's just the original function, evaluated at 0 over n factorial. 0 factorial is 1. X to the 0 power, that's 1. That gives you the first term. Then you do n equals 1. First derivative over 1 factorial, which is 1, times x to the first power. That's this term. Then you plug in 2. Second derivative, 2 factorial x squared. So that's all this notation is. It says the exact same thing. And the reason this works and we don't have to keep going all the way to infinity is that each successive term is smaller and smaller. Remember, we're around x equals 0. So this x is a small number, and when you take small numbers to higher and higher powers, the terms get even smaller. Technically, you have to check that your series converges, but that's something mathematicians tend to worry about a lot more than physicists do. Okay, let's do an example. Say our function is cosine, and we want it to approximate cosine as a polynomial. Okay, so we need to take its derivative a bunch of times. This is supposed to be a double prime. And when you start getting into high derivatives, you can stop writing all the primes and just put a little number in parentheses for the number of primes you would write. In practice, normally what you want is something like the first three non-zero terms, but sometimes your terms just come out to zero, and we're going to see that happen in this case. So that often means you need to take more than just two derivatives. Okay, so let's evaluate all of these at x equals 0. Okay, cosine of 0 is 1. Sine of 0 is 0. Cosine of 0 is 1, so this is minus 1. Sine of 0 is 0. Cosine of 0 is 1. So in this case, we actually have to get up to the fourth derivative to get three non-zero terms. So let's write that out. So we have f of 0 is 1. So the first derivative is 0, so that this term doesn't exist. So we go on to our next term. F double prime is minus 1. Then the fourth derivative term, because we're skipping the third derivative term, right, because that's 0. Let's just clean this up a little bit. So remember, you don't actually have to multiply out your factorials. You can just leave this as it is, and that's totally fine. Okay, let me know if you have any questions. Now I will give you a couple to try yourself. So I want you to find the series, the Maclaurin series, for the following functions. And I want you to find the first three non-zero terms. Once you find three non-zero terms, you can stop going. Okay, so your first one is the exponential, and the second one is sine of 3x. Alright, so pause the video and try these out. So the first thing we need to do is take some derivatives. Well, this is the easiest case we could possibly have, because the derivative of the exponential is just the exponential. Then we evaluate our derivatives at 0. Well, e to the 0 is 1. That's not changing. Okay, easy. Let's write that out. So we have 1 plus x squared over 2. Alright, not too bad. This next one is a sine, so we're going to probably need more than 3 terms before we find 3 non-zero terms. Notice I'm doing the chain rule, but I'm not writing it out. Okay, let's see how we're doing so far. So f of 0, sine of 0 is 0. Cosine of 0 is 1, so this is 3. Again, we have sine of 0, so we get 0 again. So let's keep going, because right now we only have one non-zero term. And you have to be really careful with your signs here. It's really easy when you're flipping back and forth between sine and cosine to forget when you need to flip your sign. Sine to cosine, we don't flip the sign. Cosine to sine, we do. Okay, let's see how we're doing. Okay, cosine's 1, so this is minus 27. Sine is 0. So we get another 0. Okay, we've taken 4 derivatives and still we only have 2 non-zero terms. But you see we're alternating between zeros and non, so our next term will be non-zero. Okay, now we're up to 3 to the 5th power, 243. And I'm just using the shorthand, so I'm not writing 5 primes. Alright, let's plug all this in. So our first non-zero term is the one with x to the first power. So we have 3 times x. Our next non-zero term is the third derivative term. So we have minus 27 over 3 factorial x cubed. Our next non-zero term is to the fifth power. So we have our 243 over 5 factorial x to the fifth power. Okay, let me know if you have any questions or let me know if this makes sense. The next thing we're going to look at is Taylor series. Maclaurin series are really a special case of Taylor series. Taylor series means that instead of expanding around x equals 0 specifically, you can expand around any point, not just x equals 0, but x equals a. And in practice, I usually will just refer to Taylor series and not Maclaurin series because Maclaurin series are just a special case. So we want to write out our general form. So it's pretty similar to Maclaurin series. So here, now we have x minus a that's being taken up to powers instead of just x. Instead of evaluating our function and its derivatives at 0, we're evaluating them at x equals a. We're still having our factorials in here. So you can see how x equals 0 is just a special case. And we can also write this in series notation if you prefer. And if it's been a while since you've seen this, I would recommend reviewing this notation. Let's do an example. So we're going to expand the function 1 over x around x equals 1. Now clearly we wouldn't want to expand this function around x equals 0 because this function blows up. Okay, let's get going. So I'm going to rewrite this as x to the minus 1 because that makes taking the derivative a little bit easier. Okay, let's start taking our derivatives. So our first derivative is minus x to the minus 2. And our second derivative is 2x to the minus 3. And our third derivative is minus 6 to the x minus 4. So f of 1 is just 1. The first derivative evaluated at x equals 1 is minus 1. The second derivative evaluated at x equals 1 is 2. The third derivative is minus 6. So we can plug that in. And you could clean this one up. 3 factorial is 6. 3 times 2 times 1 equals 6. Okay, that one doesn't look too complicated. And remember, each successive term is going to be smaller because we're looking at x close to 1. So x minus 1 is a small number. And a small number taken to higher powers gets smaller and smaller. Okay, now I'm going to give you a couple to try yourself. Alright, so I want you to find the Taylor series of each of these functions around the specified points. Just find the first 3 non-zero terms. Okay, pause the video and give it a try. Okay, so the first thing we need to do is take derivatives. And we've seen that when we're dealing with sines and cosines, we get a lot of terms that go to 0. So we're probably going to need to take a lot of derivatives. Okay, first 4 derivatives to be on the safe side. Okay, well, the original function evaluated at pi, cosine of pi is minus 1. You should know your unit circle. It'll go faster if you don't have to look this up all the time. Sine at pi is 0. So we're just alternating like we did before. Nothing majorly different. Cosine of pi is minus 1, so this is positive 1. Okay, we have 3 non-zero terms, so let's go ahead and write out our expansion. We start out with a minus 1, then we have the second derivative term. So then we have the fourth derivative term. All right. And if you spend any time thinking about whether functions are even or odd, you can make sure your answers make sense based on that. Cosine's an even function. You see all of our powers are even. Okay, next one. So I'm going to rewrite f of x so that's more straightforward how to take its derivative. Okay, let's take its derivative. Doesn't look like any of these go to 0, so that should be enough. And then we evaluate at x equals 25. Square root of 25 is 5. That's easy. This gives us 1/10. So these terms are dropping off extra fast. Not only is the x minus 25 going to drop off pretty quick as you go to higher powers, but the actual coefficient is dropping off really fast as well. So let's write that out. Okay, not too bad, I hope. Let me know if you have any questions in the problem solving discussion. There are some series that you need all the time, like sines and cosines and exponentials. You don't want to have to calculate those from scratch every time. You can actually look those up in the series table. And there's a series table in the pocketbook of integrals that I recommended with this course, but you can also find them online, and I'll put a link to one in eCollege. So I want to talk about how we can make best use of those tables. There's a little more to it than just looking up sine. So of course, if you just want to expand sine, that's simple enough. But say you want to expand sine of 3x. Now, yes, we already did this the long way, but we did a lot more work than we actually had to do. So another way of doing that is we can take the shortcut. So if we look in the table tells us, but instead of x, we have 3x. So we're going to replace all of our x's with 3x's. So instead of this x, we're going to write 3x. Instead of x cubed, we have 3x cubed. Instead of x to the fifth, we have 3x to the fifth. So we can rewrite this a little bit. So 3 cubed is 27. And 3 to the fifth power is 243. And I'm actually okay if you just want to write 3 to the fifth instead of multiplying it out. That's okay with me because that tells me that you're recognizing patterns. So this is the exact same answer we got before, but we spent a lot less time figuring it out. So I'm going to give you a few to try. So I want you to find the first 3 non-zero terms in the Maclaurin series. Or you could say in a Taylor series about x equals 0. It means the same thing. So the first one we have cosine of x squared, and the second one we have e to the minus 5x. I want to make sure you know where to find your series table, so you can look in eCollege. I put a link to a series table there. You can also use the pocketbook if you have that, or you can just Google series tables and you'll find more examples online. Okay, go ahead and try these out. Use the series tables to do this the shortcut way. Okay, so if you look in the table, the expansion for cosine, okay, and instead of x, we have x squared. So we're moving all of our x's, we're changing to x squared. So instead of x squared, we're squaring x squared. This can get a little bit confusing. Make sure you really think hard about what you're doing on these steps, because you're substituting x squared for x. So you have more than one x floating around. That can be confusing. So now we're substituting x squared here, so we have x squared to the fourth power. So let's simplify this. Okay, so our second non-zero term is x to the fourth power, and our third non-zero term is x to the eighth power. And you can see if you tried to do this the long way, that means you'd have to go to the eighth derivative to calculate this out. So it really is a lot faster to use this shortcut. Okay, let's do the next one. All right, the exponential is another common one you can look up in your book. And now, instead of x, we have minus 5x. So we can substitute this in. So instead of this x, we have minus 5x. Instead of just x squared, we have minus 5x squared. And we'll clean this up a little bit. This one wouldn't be too bad to do the long way, actually. But it's nice to be able to use the table to figure it out also. Okay, so that's the basic of using series, how you can calculate them, and how you can use the series table to take some shortcuts. And that's all I want you to know how to do with series. Next week, we'll be moving on to complex numbers. Let me know if you have any questions by posting in the problem solving discussion or coming to office hours.